Keynote speaker, Peter from Munich. Ray, I've known Peter for a number of years. Peter's been a passionate supporter of the International Society of Biometeorology. In fact, he's a former president of the society. Peter has also been a great supporter of the Congress, and of course we're very grateful to Munich Ray for providing sponsorship for the Congress. So over to you, Peter.
Thanks a lot, dear Glenn, and good morning to everybody. The theme of this Congress is weather and climate information for risk management. Risks are the business model of insurance companies. So risk is our business, and if we don't do proper risk management, then we cannot do profitable business. So it's very important to have this information, and actually this is also the reason why Munich Re is a sponsor, not that we look for new clients. We don't see you as clients. The reinsurers have the primary insurance companies as clients. But you provide the information we need, and so we need the exchange with you. And during my talk I will also show you that perhaps we also have some information which is valuable for your research. So, as already said by Glenn, Munich Re is one of the leading global reinsurance companies, and part of our business is to cover risks of natural hazards, and a lot of money is involved, as you can see, with losses like Hurricane Harvey. Now people discuss that it can be above 100 billion US dollar loss, and the reinsurance companies pay quite relevant amounts of that. We have started more than 40 years ago to collect data, global data on natural events which have caused any kind of losses. This could be material losses, but also human losses. And we focus on the property and personal damages. The loss development of each event is continuously updated, so if we get new information, then we update that. Just recently, in the last years, we have added around 1,000 events every year, analyzed that with a focus on the economic, insured, humanitarian losses, and this database certainly is a basis for internal risk assessment at Munich Re, but also we provide detailed information for different stakeholders. Research definitely is one of the stakeholders, the scientific society, but also political decision makers are also targets of our information. Currently in this database, which is called NatCat service, has 40,000 events, around 40,000 events are documented. Let's have a look at the different perils. And there are three peril families which are categorized according to the origin they have. There are the extraterrestrial ones, which could be meteorites falling on this globe once in a while, solar storms disturbing the electricity support, for example. There are the geophysical ones, which have the origin in the Earth's crust, like earthquakes, volcano eruptions, and tsunamis. And then we have the weather-related ones, the storms, floods, hail, lightning, landslides, and some others. There's a big difference between the first two of these peril families and the third one. The difference is that, as far as we know, currently there hasn't been any anthropogenic influence on the hazard side for the extraterrestrial and geophysical events, but there is increasing evidence that there is an anthropogenic influence on the hazard side on the weather-related events, so there is a risk of change. If we have a look at the development of these events, and here you see the global number of loss-relevant events since 1980. You see the different colors, geophysical, meteorological events. These are the windstorms, hydrological events in this case are the flood events, and climatological are other weather-related events like extreme temperatures, droughts, and forest fires. You see there has been a significant increase. This is the first thing we see, that is about a factor of 3 times as many events recently compared to the early 1980s. If you look at the red bars only, you don't see this significant trend. So the perils which come out of the Earth's crust, they have some fluctuation from year to year, but they don't show a trend upwards, not a relevant trend, as what we see for the weather events. So changes in the atmosphere must be some drivers of these increasing events. And we see increasing losses, and what you see here is the inflation-adjusted losses. Green, the overall losses, so this is the total economic loss, and blue are the parts of these losses which have been covered by the private insurance industry. So this is different from year to year. It depends on where these catastrophes happen. In industrialized countries, a larger portion is insured compared to the developing countries where hardly anything is insured, but in general, with a high volatility, you see an increase in these inflation-adjusted losses. If we deal with the analysis of data and make it comparable in different times, then we have to regard two biasing factors which we have in our loss data. One is the reporting bias. What does it mean? There's a hypothetical curve of all loss events, so we have the losses on the x-axis and the number of the events on the y-axis. So we have many small events, you have a few big loss events. In the past, before the internet era, we perhaps had a coverage of what you see here. The smallest events we didn't cover because we didn't get information from Africa, from South Asian countries, or other countries. Today we get more information, but we don't still get all the information we need. So the best thing to avoid this bias is to cut the statistics or to cut the lowest loss events off, so we can reduce this bias, reporting bias. And we have another problem. We have not only inflation, which means the loss of value of the money, but we have increasing wealth. And we have increasing population, and there are more destructible assets. So, for example, in the past, this curve has looked like this, and due to exposure growth now, it looks like that. And we also have to somehow consider that if we make losses comparable. So let's see how we do that. The first thing is we have a classification of the intensity of these loss events, and we classify this in 5 groups. There is a group 0. These are just some extreme weather events with hardly any losses. Then we start with catastrophe class 1. And we distinguish between different income groups, because 100 million loss in Bangladesh definitely means something different from a 100 million loss in the United States. And we differentiate that by the income classes, World Bank income groups. So, for example, to get into the largest loss intensity group, you need 3 billion loss in the industrialized countries, 100 billion loss in the poorest countries. So, by this, we assign every event an intensity class, and then we can only analyze events of a certain intensity class and cut off, for example, the lowest classes. What about data normalization? And this actually is the thing to do to make the losses comparable. It tries to account for changes of wealth and destructible assets over time and space. And it's more than inflation adjustment. Inflation adjustment is just that you consider the increased value of a house because the money has lost some of its value. So a $200,000 house in 1980 perhaps today would cost $500,000. But in the meantime, perhaps there is not at the same location one house, but there are 2 houses. So you have to, if you normalize the loss, and which means that you calculate how high a loss would be with a historical event happening today, then you see that the factor is not a factor of 2.5 like for the inflation, but it's a factor of 5 now, because the values have grown which are at risk. So with the inflation adjustment, you answer the question, what would the loss of an event X in the year Y cost today? And with normalization, you can say what loss would the event, the historical event, cause in the past year Y cause today. And this is the thing we do. So we have normalization of all our data available, and I will show you in the end that you even can access this online. So let's have another look again at the loss curve I've shown you already for the inflation adjusted values. Here you see the nominal losses of all worldwide natural disasters since 1980. If you adjust them for inflation, you see they go up a little, especially the earlier years, to the earlier years when you get. And if you normalize them now, you get a surprising result. You get the surprising result that since the late 1980s, there hasn't been any change in the normalized losses. So many people, like for example Roger Pielke in the US, say, okay, this is proof climate change or changes haven't done anything, so we don't have to be scared, we don't have to bother. But we really have to look a little deeper in that, because there are some compensating effects in this red curve. There are some losses which have gone up, even normalized losses, and there are some losses which have gone down. I show you first the ones who have gone down, and this is really good news that losses are decreasing, losses caused by natural disasters. And these are the losses caused by floods, especially for river floods. On the number, on the frequency side, we see a strong increase. We have more intense precipitation events. We have more events which have caused some kind of loss. But if we look at the normalized flood losses, you see there have been real huge losses, especially in China in the 1990s. And if you cut this curve at 1990 or so, you would get a decreasing trend of losses. So what's behind that? We have more events of extreme precipitation, but we have decreasing losses. The answer is investments into prevention. There have been huge investments into river flood prevention. I show you a few examples. I start in Hamburg in Germany. There has been a storm surge in 1962 causing losses of 1.5 billion euros. And since then, about 2.2 billion have been invested into flood protection measures in the city of Hamburg. Since then, 9 times the river level has been higher than 1962, and hardly any loss has occurred anymore. So the investment of 2.2 billion has paid back manyfold. We have calculated roughly it has avoided losses of about 20 billion euros. Another example now from China. In China, there has been a devastating flood in 1963 in the Hoeppe, I don't know whether I pronounced that correctly, river basin. You see Tianjin here on this photo. In 1963, the loss has been 13 billion yuan, and there has been a similar flood in 1996. Also, the absolute level of the loss has been much lower, with 6 billion yuan. Why this? Because enormous investment into flood control has been made in the meantime, and you see how this looks with all these dikes which have been erected and constructed to avoid the losses. In 2011, there has been a real drastic Mississippi flood, but there had been a Mississippi River and Tributaries project of the Army Corps of Engineers in the United States, and they have calculated that by these investments, more than 100 billion US dollars of losses have been avoided by these investments into flood protection. And it's not only the flood protection, but also houses can be built more safely. There is one good example, which is the Insurance Institute for Business and Home Safety in the US. They have a huge wind tunnel. Here you see the photos of the wind tunnel. They can put whole houses into the wind tunnel and create wind velocities of 180 kilometers per hour. So this is a category 3 hurricane which they can create. You see that many fans which are doing that. This laboratory is located in South Carolina, and I will show you just a small video on that. They have constructed 2 houses, have put these 2 houses into the wind tunnel, and in one house they have applied some measures costing about 5% of the whole construction costs of the house to make to fix the roof a little better and to make things less vulnerable. And in the video now you will see how this. So let's start the storm. It has been 160 kilometers per hour wind velocity. One house is totally gone, the other is almost without any damage. The only difference in investment is 5% of the construction costs. So by relatively little money, a lot of losses can be avoided. And actually, Munich Re, our branch in the United States, Munich Re America, together with this institute, has released an app which you can use on your table if you build a house. It's called Fortified Home, where you can learn what you can do to make houses less vulnerable against weather-related perils. Now let's go to another peril, which we see some really relevant increases also in the normalized losses. And these are the so-called convective events, thunderstorm-related events like tornadoes, hail, intense precipitation. And there we see significant increase in the number of the events. This is the global picture of the number of relevant convective storm events. Relevant means loss relevant. And you see that here also the normalized losses are going up. So you cannot explain the increases in the losses just by socio-demographic, socio-economic measures. You have to look for other explanations, and this could be on the hazard side. So this is the global picture, and this is the picture in Europe, where we see this increase, especially in the last 10-15 years, and we see a similar picture in the United States. So this is interesting that this seems to be a global phenomenon, that losses, normalized losses of convective events go up. So what may be the process behind it? Certainly the increase in humidity in the atmosphere plays an important role, because humidity, water vapor, is the fuel for these convective loss events. And here you see a study which was published a few years ago, where just the routine measurements of meteorological measuring stations have been evaluated, and there has been a trend found on a specific humidity. Wherever you find these blue colors, there has been an increase in humidity in the last couple of decades, and where you find these black dots, this increase has been significant. So almost the whole northern hemisphere, in the whole northern hemisphere we find these increases in humidity. We have more water in the atmosphere, which means there can be higher precipitation levels, there's just more water available, and we have more energy in the weather machine, in the weather system. And where does this water come from? Yeah, it comes from the warmer sea surfaces. The sea surface temperatures have increased significantly all around the globe. Here you see them in the tropical basins where the tropical cyclones are generated, and you see in all of these basins there has been a significant trend of increases. The only explanation for these increases, as this is a global phenomenon, not depending on ocean basin natural climate oscillations. The only explanation is that global warming is playing a role on that. Just one example which is backing this hypothesis or theory is a thunderstorm which has happened in June last year in the Netherlands. It has been a €1 billion loss event, 1.3 billion total losses. Many greenhouses have been destroyed by this hail. You see one of these hailstones here in the hand of this person. And interestingly, and this is the most important information here, this has happened on the day where the highest humidity level has been measured in history in the Netherlands. Since we have documentation of that, there's been a dew point temperature of 25 degrees Celsius. Never before it has been as high. So this backs the hypothesis that the increase in humidity plays an important role in that. So let's summarize the drivers. Why do we have to expect that losses caused by natural disasters go up? Even without climate change, without any change on the hazard, we would have to expect that. One reason is population growth. If you look at this curve now, about 7.3, 7.4 billion people live on this earth. You don't have to go far back, just about 40, 50 years, then half of the people lived on this globe. So double as many are affected by natural disasters. People have to settle in more risky areas because of the pressure, population pressure in many densely populated countries, so this drives up the losses. Then it's the rising standard of living, that people are more wealthy, so there are higher values at risk which can be destroyed. People concentrate more and more in cities, which can be also more vulnerable, which don't need to be if they are planned properly, but can be more vulnerable against natural disasters. So in 1975, there were only 3 megacities on this globe. In 2025, it will be 28 megacities, which is cities with a population of more than 10 billion people. And people tend to want to live in risky areas, like, for example, Florida. Here you see Miami Beach in 1926 and 2015, an area which has been affected by hurricanes for all times. But if hurricanes become more intense, then this also means that this is a loss driver. Here, for example, in Thailand, where they built this semiconductor factory right into a floodplain, which has resulted in the most costly flood event in history on this globe in 2011, with a total loss of about 40 billion US dollars. Yeah, and then there is another loss driver, and for the convective events, we are quite convinced that we see that already in the data. This is climate change. Climate change, as you know, has set records during the last 3 years. Each of the last 3 years has been a record year. Now we are 2017, and this is NOAA data. Again, it's so important to have NOAA, and we are very much supportive also that you get funding to provide the data. This is NOAA data, and the latest data you have published are the data of July. The August data are not published yet, but it has been the second warmest again, and 2017 is on track to become the second warmest after 2016. And we know from IPCC that climate change definitely is increasing the risks of weather-related extreme events. Sea level rise will contribute to that. By the way, Lloyd's has calculated that about 30% of the storm surge loss in Manhattan due to Sandy in 2012 is due to the fact that the sea level is 20 centimeters, just 20 centimeters higher than it has been 100 years ago, and these 20 centimeters are global warming related. So 30% of $1 billion loss already due to the fact that sea level has risen. So more frequent and severe extreme weather events are projected for some regions. We have to be sure that not every natural disaster like Harvey is climate change related. Perhaps the intensity of the precipitation may be, but the statistics show that things are changing, patterns are changing, and part of these changes may be related to global warming. I get to my conclusions. The nominal losses caused by natural disasters have increased in the last decades. This is something we have to expect also in the future. The main drivers are population growth, increasing wealth, and number of people living in regions with elevated natural catastrophe hazards. While hazards of geophysical and extraterrestrial perils are not changing, the hazards of most weather-related perils are influenced by global warming and thus changing in the long term. For the convective events, we think we already see that in the past. For losses caused by these convective events, especially in the US and Europe, there is a suggestion that climate change has already been a relevant factor. But, and this is the good news, and we definitely should convince our political decision makers also to do these investments for the future, because by ambitious and smart loss prevention measures, increases in losses can be dampened or even inverted, like we see that for the river flood losses, even when the hazard increases. Yeah, my last slide is this one. You see an internet address, the blue one. If you click on that, you get free access without any registration to our NatCat service analysis tool. You can create your own graphics, be it the frequency of events, be it losses, normalized losses, inflation-adjusted losses. You can select regions, you can select perils, and you can use this wherever you want in your publications, in your presentations. Just check it and give us feedback if you find any mistakes or if you like it. So this has been released in April this year. It's brand new. And this is part of the service by which we want to give back something of the things we get from you, from the scientific community. Thank you very much for your interest.